Hello everyone, and welcome to class number 29 of Physics 218. So last time we talked about a couple of things. So we talked about interpreting the expansion coefficients in the expansion of an arbitrary wave function as a sum of stationary states. Right? We talked about how the coefficient modulus squared represents the probability of measuring the energy to be E sub n, the m infinite square well energy. That led us into a discussion of eigenfunctions and eigenvalues, and we hinted a little bit about what those have to do with measurements in quantum systems more generally. So today, what I want to do is the following. We've now quite thoroughly explored a very important quantum system, the infinite square well, that has had a lot to teach us about how quantum mechanics works. I want to take everything that we've done so far and sort of summarize and restate this in terms of general principles of quantum mechanics. And sort of where we leave off from here is kind of where you'll pick up from in Physics 421 if you go and take that the next time it's offered in 2 years. I also want to spend some time mentioning some of the interpretive issues that come up in quantum and thinking about, well, what's going on here and what does this all mean? There are some really deep questions that we haven't quite had the chance to explore in depth. And frankly, if we were here together in person, I think we would have had some very fun discussions about interpretation, but I'll try to say a few things and point people to some resources for further exploration. And then I'll give a hint as to what's coming next as we head into Chapter 4 of Townsend starting on Wednesday. So I want to turn now to recapping what I call the general principles of quantum mechanics. There are some textbook writers who would go so far as to call these postulates of quantum mechanics, in the sense that they underpin the whole theory and can't really be rigorously derived from something else, in the same way that we might talk about Euclid's postulates in geometry. Now, the most we can say is that these ideas are consistent with experiments, and sort of that's the route we've taken. We started off by thinking about the wave nature of matter as thinking about experiments like doing interference with particles, right, and thinking in terms of the sort of wave-particle duality of matter as introduced by de Broglie. But sort of that sort of somewhat ad hoc reasoning can kind of lead you to sort of this set of postulates or principles. And so the first principle that I would state is the following, that in quantum mechanics, particles are described by a wave function psi of xt. Right? So a few things about the wave function. You know already, right, that what the wave function directly tells you is something about the probability of locating a particle between two locations, right? So what this tells you is that the prob of finding particle between A and B, sort of a clunky way to write that out, but is given by the integral from A to B of the probability density, which is, as you know, the wave function modulus squared. Okay. Now, just one sort of thing to remind you about, right, just because a particle's wave function is extended, right, doesn't mean that the particle itself is sort of smeared out or spread out over space. What the wave function and indirectly the probability density tell you is just about the probability of locating a particle. Now, we've learned how to calculate and find other things given the wave function. And what I just want to emphasize is that sort of the wave function contains all the information we have or can have about the particle. So we've seen recently, for instance, how if I give you the wave function for a particle that's in the infinite square in an infinite square well, you can use it to figure out, for instance, what the probability of an energy measurement might be. Okay. So principle number 2 is that physical observables, so things that you can measure, correspond to operators. So the important ones we've talked about thus far, right? We've talked about position, and the position operator x hat takes the form, and that's what I mean by with the arrow here, takes the form x. We learned that the momentum operator takes the form minus I h bar partial x. And then we can also build other operators by combining these in suitable ways or multiplying by constants. So we have the Hamiltonian or the energy operator taking the form px squared over 2m plus a potential energy that could, let me actually make that an operator that is in principle could depend on position. Okay. So we will be able, as you go on in quantum mechanics, to introduce other operators. So depending on how much time we have in this course, we may take a little bit of a look at quantum mechanics in 3 dimensions, particularly as it applies to the hydrogen atom. And if we go there, what we'll see is that we'll introduce operators for angular momentum, which turn out to be really important. Kind of a coincidence that I dragged this t-shirt out of the closet today. But yes, so physical observables correspond to operators. Principle number 3 tells us about measurements of an observable that correspond to some operator that I'm just going to call A. So what we've learned is that the only possible results of such a measurement are one of the eigenvalues of A. And moreover, the probability of measuring that eigenvalue, so getting a result of a measurement with that is eigenvalue A, is given probabilistically by the following. It's given essentially by the expansion coefficient modulus squared, or the modulus squared of the inner product of the associated eigenfunction with our wave function psi of x t. So the best example of this, hands down, is energy, right? And that's what we spend so much time and effort on with the infinite square well, right? We talked about how we could expand any arbitrary wave function in an infinite square well in terms of a sum of energy eigenfunctions, or stationary states. And then we talked about the probability of getting a particular value for the energy of the system, right? And that's what turned out to be the expansion coefficient modulus squared. And as you did on the homework, you found that expansion coefficient by taking this inner product between the energy eigenfunction and the given wave function. I've written psi of x t here for generality, but the result still applies if we're only considering the spatial part of the wave function. So energy is the best example of this, but this also turns out to hold for all other operators in general. Now, it's less obvious how this holds for position and momentum. Part of the difficulty is that the position operator has a continuous range of eigenvalues. So the position operator can have eigenvalues continuously from x equals minus infinity to x equals positive infinity. And the same can be said for momentum. So we didn't really see this until we got to our first operator that has really discrete eigenvalues, namely the energy operator or the Hamiltonian. It's also less clear how sort of this inner product applies in the case of position or momentum. But I can assure you that it does. That is a discussion I think we're going to have to defer a little bit to Physics 421. If anybody is dying to know more, I'd be happy to talk about it or maybe make a bonus video. But for now, maybe all I'll say is that it turns out that when we write the wave function explicitly psi of xt as a function of x, it already kind of is an inner product. Between sort of a more abstract quantum state and the eigenfunctions of position. And I'm just going to abbreviate eigenfunctions as EF so that to not have to write that out. So yes, I'm being a little hand-wavy here, but this formalism still applies. One other point I'd like to raise about principle number 3 is expectation values of operators. And what we've learned is that the expectation value of some operator A turns out to be given by the following. Right? We take the wave function, complex conjugate it, we sandwich the operator in the middle, multiply by the wave function again, and then integrate over all of space, right? We've seen this for position, that's where we first started to talk about it. We've seen this for momentum, and it also holds for energy. Now, the general proof of this result turns out to be a somewhat tricky one. It's easier to do it for operators that sort of have a discrete set of eigenvalues. You'll, I think, go through that proof in Physics 421. We have sort of come at this via arguments that suggest plausibility, right? So for position, this isn't so implausible just from thinking about how sort of expectation values work and thinking of psi modulus squared as a probability density. For momentum, right, we had to invoke Ehrenfest's theorem, which is sort of the idea of don't break classical physics more than you have to, such that your expectation values still obey classical physics. But that was sort of a sort of ad hoc idea we had to invoke to get the form of the momentum expectation value, and then we sort of just claimed it applied to energy, to the Hamiltonian. Again, 421 will do a more general proof of this result. So principle number 4 of quantum mechanics is that time evolution in general, except with one exception, except during measurement, is governed by the Schrodinger equation. This is sort of where we started it back in chapter 2. You know now what the form of the full time-dependent Schrodinger equation is. Now that we've learned about operators, but I can simplify this a little bit to say that it's the Hamiltonian operator acting on my wave function gives rise to its time evolution. T, D, T. Now, in practice, right, what we usually do to solve this is we do what we did, we apply separation of variables. Apply right, and that is what leads us to the time-independent Schrodinger equation. Right, which turns out to be an energy eigenvalue equation. I'll write the whole thing out. Right, so it ends up being so the solutions to the time-independent Schrodinger equation, right, are states with definite energy E sub n. There's an associated solution or wave function or stationary state, right, psi sub n. And let me summarize. So this I can rewrite as a Hamiltonian acting on one of the solutions, giving me the energy eigenvalue E sub n. So the solutions to the time-independent Schrodinger equation are called stationary states. I'm going to erase the board and remind us of their properties. So to remind you, the solution psi sub n of x of the time-independent Schrodinger equation, we've called them a couple of different things. We started by calling them stationary states, and then last time we learned that they can also be thought of as energy eigenfunctions or energy eigenstates. So just to remind you, right, these are states that are eigenfunctions of the Hamiltonian, right? They have definite energies E sub n. Okay, and moreover, they time evolve in a very specific way. Oh, one more thing. They also form a basis. That's complete, and also just that you can represent any wave function, right, in terms of a sum of energy eigenfunctions, right, and that this time evolves in a really specific way. And remember how we first started calling these stationary states because the associated probability density ends up being time independent. So in general, right, so the general plan is to, and this is a plan we'll continue pursuing in the next chapter. We're going to solve the time-independent Schrodinger equation for different potential energies, and a lot of the physics will end up coming from the application of some suitable boundary condition on the wave function. So in the case of the infinite square well, remember, the boundary condition was that the wave function had to vanish at the ends of the well at 0 and L. Principle number 5 is, in my opinion, probably the strangest principle in quantum mechanics, and that is the idea of collapse. What this says is that if you have a particle and it's described by some wave function, capital psi, and you go and you make a measurement that corresponds to some operator A, and you get, as a result, the eigenvalue little a, then what happens to your wave function immediately after that measurement is that the wave function immediately becomes the associated eigenfunction psi sub a. So this is really weird in the sense that what this suggests is that measurement changes the system that you're measuring. So we've talked a little bit about one example of this, right? So we talked about how if you have, so let's say you had like a wave function that was not localized. So let's say you had, let's say we were in the ground state of an infinite square well, right? And then I measure the particle to be at I measure the particle and I find it at some specific location. Well, right after that measurement, we talked about how the wave function collapses to a single sharp spike, right? And I showed you that in a computer animation last time, right? And because that spike is not an energy eigenfunction, right? Then the subsequent time evolution of the system becomes complicated, right? So we've seen this. But this comes up maybe just as even more strongly if, let's say, I had initially a wave function that was in some superposition state of energy eigenfunctions. So suppose, for example, that I had a wave function that was given by just an equal superposition of energy eigenfunctions, or stationary states, right? If I were to take this wave function, right, that's a combination of the ground state and the first excited state, if I go and I measure the energy, if I measure the energy and I get the energy to be the ground state energy E1, and I think you can see from this superposition that I have a 50-50 probability of getting E1 or E2. I get E1, my wave function suddenly becomes the ground state wave function. And the same thing applies if I were to measure the energy and get the result E2, I would collapse the wave function to psi sub 2. Now, if this seems strange, it totally is. So there are many physicists who have spent time trying to think about what wave function collapse really means or has to involve. Maybe you'll contribute to that understanding at some point. But what I want to say for now is that if you think this is weird, you're totally in good company because it is strange. Now, there's something that's sort of even stranger that maybe this suggests, right? So, I told you, right, that for a position measurement, right, if I start with a delocalized wave function and I measure its position to be somewhere, I'm going to collapse my wave function to a spike. So I'm going to just draw a picture of this. So let me erase the bottom part of the board. So consider the following, right? So suppose we started off with some wave function that looked something like this. It was delocalized, right? And then we went and we measured the position of our particle. Okay. If we make a position measurement, right, there's a range of there's a probability for measuring it somewhere. You know, we'd be probably most likely to measure it around here, but there's a non-zero probability of measuring it like over here or over here. Now if we measure it, and let's just, for sake of argument, suppose we measure it like right here, what we end up with, right, is that we collapse the wave function right to a spike. Let's just say that the wave function looks something like this. Now, if you saw from the animation from last time, right, in general, position eigenfunctions are not energy eigenfunctions. So there's some complicated time evolution, and what happens is that spike sort of immediately starts to spread out. And so let me just, so later, so a very short time later, right, this maybe has started to spread out a little bit. But, right, suppose we measure the position again, right? We're most likely to measure the particle to be near the same position we originally measured in. Right, so I should have used a green arrow, but if we make another position measurement, right, we're going to once again get a spike. I think you can sort of see what I'm getting at. If we can keep on making repeated position measurements fast enough, we might be able to sort of indefinitely localize our particle to a very small region around where we originally measured it to be. So the idea that you could localize particle by so this idea that you could trap something by just measuring it over and over again very quickly, and you have to do it very quickly so that otherwise the wave function sort of starts to spread out. This idea that you could sort of trap a system by measuring it over and over is something called the quantum Zeno effect. Okay. Now, you might think this is completely crazy. That that this is a totally just like unbelievable idea. Surprisingly, you can do experiments to test this idea with atoms, and the results of the experiments are that quantum mechanics works the way we think it does. Namely, we can do experiments that are consistent with this picture that I've drawn of being able to sort of indefinitely hold a system in a particular state by repeatedly measuring it. I'm now going to cut to my computer where I'm going to go back to a PhET simulation from that we looked at a while ago and bring up some of the things that come up, including the quantum Zeno effect that in the simulation. Now that you know a little bit more about quantum mechanics and have the capacity, I think, to really appreciate what's going on. So I just wanted to show you all some things with this quantum wave interference PhET that we looked at a couple of weeks ago. So I'm going to select the single particles tab right here. And just so that we're talking about particles, I'm going to switch here to electrons. So right now I'm in this mode right where I can fire sort of one particle at a time. Now that we've learned a little bit more about quantum mechanics, right? So what we're actually getting here is a wave packet when we fire one of these. So right now we're plotting the magnitude of the wave function, but you can see it's sort of wavy nature if we just plot the real part, or if I switch it to the imaginary part. And so, for instance, if I increase the velocity, I should shorten the de Broglie wavelength. So let's see if that looks a little shorter compared to when I slow the particles down, and I definitely have a longer wavelength there. All right, so let me just sort of put the velocity back sort of towards the middle there. I'll clear the screen. Now we can create a double slit situation here. I can move the barrier around. I'll make the slits a little narrower also. And as we talked about in class, right, we can think about building up sort of an interference pattern, one particle at a time. But that's actually not what I'm going to focus on here. So I'm going to focus today on adding a detector. So right now, so this is a little bit tricky, but right now this is in auto detect mode, so it's going to periodically make measurements. I'm just going to step through this slowly first to show you what it does. So I'm going to turn off the auto detect, and I'm going to fire, and I'm going to actually, let me just scooch this up actually a little bit so that, so I'm going to fire an electron, oops, and then I'm going to step through time. So right now, so what's going to happen when I right now is if I click detect, right, there's a small chance that I'm going to, just based on what the where the wave function is, that I'll detect my particle within this box. But more likely than not, I won't. And the way the simulation works is if you don't detect the particle inside the detector box, that's still a measurement. The wave function does change. It collapses to sort of being zero within my box here. So if I keep marching forward in time, now we've got so the wave function has sort of gotten back in the box. Let me fire another particle and see if I do another measurement. And I'll detect no, but I didn't, etc. Again, my wave function has collapsed to be outside my box. I'm going to now turn on this auto detect mode so that we just get continuous detection, and I'll just let this play now. So I think you have a better sense of what's going on. But there's one really wacky and cool thing that I want to show you, namely that quantum Zeno paradox. So I'm going to sort of make this detector just a wee bit bigger. So then I'm going to put it over one of my slits. I'm going to turn on this repeat detect feature so that the detector will keep making measurements pretty rapidly. And let's see what happens. Ooh, we got it right there. So notice how the particle was essentially, the wave function was more or less confined to the box by those repeated measurements, right? Where we measured it inside the box, the wave function collapsed, it started to spread again, but then we did another measurement and actually held it there for a while. Let's see if we can't do that again. This is totally probabilistic, so might take a few tries. There we go, there we go, there we go, there we go. Yep, so that's sort of an illustration of our quantum Zeno paradox, and it's very different than the situation if we have no detectors at all. So there's one more thing I wanted to show you with this FET, and that we didn't talk about when we talked about interference for particles a couple of weeks ago. So I've set the gun here to be shooting electrons again. I'm going to set up double slits here. I'll move the slits further down. Let me make them close together to spread out the interference pattern. And if I turn this on, as you know, right, we're going to end up seeing an interference pattern on the screen, right, where we have a bright central fringe, we have this minimum here, and then to maximum. Maybe I'll just make the slits a little wider to bring those. Yeah, okay. Now you can clearly see the two the first order maxima here. But what we didn't talk about before was what happens if you put a detector in place. It turns out if you put a detector on either one of the slits, right, the interference pattern goes away. That is, if you know what path the electron followed from here to the screen, you don't get any interference effect. Right? This is sort of like what we talked about with the single photon Mach Zehnder interferometer experiments we started talking about with light, right? Where the only time you get these interference effects is if there's more than one path that the photon can take, and if you don't know which path was actually followed. So same thing turns out to apply for particles, and I think one of the takeaways, this goes back to measurement in quantum physics does something really weird. So if I put a detector on the other slit, I once again destroy that interference pattern.